Большое спасибо. Я очень рад быть тут в Яндексе, в России. Как Андрей сказал, я был в России в 1977 году. На 3 месяца тогда я был в Москве. Я был приглашен в Институт математики имени Стеклова. Но потом я не говорил по-русски. Я очень много забыл. Это было уже 36 лет тому назад. Так ничего не поделаешь. Я думаю, что вот мои слайды все по-английски, а так я могу больше говорить по-английски. Я комбинаторик, я могу сказать, что я ученик Эрдоша. Почему я стал заниматься с комбинаторикой? Это просто потому, что проблемы это очень так простые. Я думаю, что для математики это очень важно иметь проблемы, которые, если вы имеете 10 минут, вы можете объяснять, какому математику вы хотите. Это, конечно, для развивания математики очень сложные, нужны очень сложные теории, как алгебраическая геометрия или так, но вот большинство проблем, они начинались так очень простыми проблемами, так, например, как сказать, это prime number, twin prime problem. Гипотеза Гольбаха, каждое парное число можно таким образом писать, где А то Б prime numbers. Но надо иметь такие вопросы, которые очень простые. А потом люди хотят решить эти вопросы, а за эти они 10 лет, 20 лет работают, а изработают очень большой арсенал сложных оружений. Но я стал заниматься комбинаторикой, когда я слушал доклад Пола Эрдоша. У него были всегда очень простые такие проблемы. Простая проблема это не значит, что это очень легко решить проблему. Я вам буду говорить об таких проблемах. Так, уже там на слайде это есть, что я моя специальность математики, это значится, это называется экстремальная теория множеств. Это все такие finite sets. Таким образом, x это конечное множество, у него есть только n элементов, 1, 2, 4 и так далее, n. Вот 2x это все фамилия всех подмножеств, это множество power set. А xk это все k-элементное подмножество. Таким образом, если у нас есть фамилия множеств, это просто подмножество этого множества. А если все одинаковые, называется k-uniform. А вот в моей области одна из первых теорем была теорема Erdos-Ko-Rado Theorem. Это мы имеем очень простое условие. Условие это intersecting. Значит, пальцо не очень маленький. Надо вот пользоваться с этим, да. Intersecting. Это значит, что всякие две множества имеют такое non-empty intersection. Erdos-Ko-Rado Theorem это уже Erdos, вот они писали работу в 1961 году, но 20 лет позже я s Mikail Deza мы писали работу теорема Erdos-Ko-Rado 20 лет позже. Я дал этот тайтл, потому что в Венгрии есть одна очень красивая стиха, которая называется 20 лет позже. Поэтому я дал вот этот тайтл, но название. Но когда Эрдош видел эту статью, он сказал мне, что это неправда. Их теорема уже доказана в году 1938. Тогда он был в Англии, в Великой Британии. Он работал вместе в теории чисел, так вместе с Ко, а там множеств, теория множеств Радо, они тогда нашли эту теорему. Но в то время никогда не интересовался законами теории, потому что они не писали вот эту статью. 23 года позже они писали, а вот это очень основная теорема. Что это значит, что эта теорема нам скажет, это если у вас есть такая одинаковая K-uniform, фамилия, семья, если вы хотите, но множество, гиперграф даже называется, K-uniform гиперграф, у которого no empty intersection, но самый большой, вы можете возьмить, это просто n-1 choose k-1. n-1, k-1, это, конечно, это просто, так, например, вы возьмите одну, все подмножеств такие, что один есть член этого множества, элемент этого множества. Тогда, конечно, две множества будут так иметь не пустое intersection. А у этой теоремы есть несколько доказов, но я хотел немножко сказать вам об новом доказе. Это я нашел вместе в Фюрере. Товарищ мой от университета в Будапеште, он теперь в Америке. Но какое доказательство? Но каждый человек, если есть математическая проблема, а если найдет свое доказательство, он очень рад, а думает, что вот это самое хорошее доказательство. Конечно, лучше, чем доказательства других. Но как можно сравнивать доказательства? Я вам скажу маленькую историю об числах, не об числах, об математике, или как сказать. Вот, вы, конечно, знаете, Вавилон, это теперь Багдад, это был там Ирак. А в то время уже люди умели писать. Но еще чисел не было. Но они умели писать и писали много. Есть, мы можем еще сегодня читать, что они читали. Но надо знать язык. Я, конечно, не знаю этот язык, но я читал об этом. И кажется, у них в то время, более-менее 500 лет тому назад, у них еще не было чисел. Но они уже делали бизнес. и все. Как называется это? Этот зверь, домашний зверь, 4 его, белый, как, это не конь, это у него есть вот это. Это там в горах живет, кушает. It's eating grass. A sheep, not a sheep, no, a goat. Козел. Okay. Козел. Но у них были козелы, а был там человек, у кого работа была взять козелов у богатого человека, их повозить в горы или куда-то, а потом надо было вернуть козелов. Как? Пастух, так. Вот пастух, если нет чисел, возможно, что пастух, он украет. Пастух. Если вы знаете, что у вас есть 127 козеров, но очень просто, возможно, числить. Но у них не было чисел. А что они делали? Они просто, вот там был богатый человек, а был пастух, а богатый человек послал вот козер от дома, а пастух, он положил, когда козер вышел, он положил такую ташку или что, камень, маленький камень. Для одного козла один камень. И вот когда все вышли, они вот уже умели, там у них была такая техника, чтобы заключать эту маленькую ташку. Нельзя открыть. А вот они положили там. А когда пастух вернулся, они открыли ташку. А наоборот, когда козер входил, они взяли один камень. А если камень не было, когда все, конечно, если все вернулись, тогда на крае не было камня. А вот они пользовались этим методом. Это открыто, там, это писано там, так, 5000 лет тому назад. Значит, что это проще, чем числить. Вычислить или как. Но, вот, я извиняюсь, так долгое время я говорил об этом, но вот мое доказательство с Фюреди, это такое доказательство из вавилонских времен. Значит, не надо числить. Значит, мы хотим доказать просто, что у нас есть эта фамилия, а есть вот эта фамилия, все подмножия, которые имеют один как член, а возможно найти такое, как сказать, отображение, как map. Отображение с F на F0. А так, если не надо на вес F0, но в F0. А если у вас есть такое отображение, ну, конечно, у вас есть тогда доказательство для теоремы Erdos-Ko-Rado.
So the notation is different. There is F1 or F0.
Oh yeah, you are right. Я писал это неделю тому назад, а вот, вот тут я писал F1. Ну вот. Спасибо. Ну а как это делается? Это очень простым способом. Ну вот, возьмем, как я писал, F0, F1 на слайде, подмножества, в которых есть. Но вот это F1 ничего не... Я должен был тут... у нас тоже есть уже техника, не надо пользоваться рукой. И один. А вот. Значит, все это не надо. What happened? I pushed it, I'm sure. I didn't want. So first we divide F into these two parts. Let me say it to make faster in English. In two parts, those sets which contain one and those which don't contain one. So this is the final definition for F1 and F sub 0. And what I wrote on the whiteboard is A sub 1. So, and then I want to make a one-to-one map from F into all the subsets of, so actually it is not even this one, but it's never mind. It's about it's the same size, but I use them in a different way. I just take the elements which, I take away the element 1 from all the sets. So all the k minus 1 element subsets of 2 to n. So this n minus 1 element subset and all these k minus 1 element subsets, that's what I'm taking. And I try to make such a map. And how we proceed, it is really just surprising that it works. Namely, for F1, the sets which contain the element 1, I just take the map that for each of them, I just remove the element 1 from them. And what shall we do about the elements, about those which don't contain those sets which don't contain 1? So they are all, of course, subsets of 2n. K-element subsets in 2n. And I am going to list them. And I'm also going to list all the k minus 1 element subsets, let's call them, if I had no other than G, maybe, yeah, G. And these are the subsets the k minus 1 element subsets. And I define a matrix here, namely I put 1 if G is and F have empty intersection. That is the matrix I define. Oh, sorry, I shouldn't move so much. So it's, and then what we have to show actually is that this matrix is having full rank. I put on the whiteboard, I made the rows and columns in a different way, so I have to show here that it has full column rank. And actually there are some columns which are completely zero in this matrix. And exactly each of these sets which is of the form F minus 1, where F was in our family and 1 was contained in F. For each of these sets, F minus 1, that will be, of course, here among these sets, it will be completely zero this. Why? That's the condition. Our condition was that we should have an intersecting family. So intersecting, it means that F minus 1, it means that F intersection is G, it cannot be empty, because if it was empty, then F that didn't contain 1, so we would put back the element 1.
Sorry, the matrix is made, the columns are indexed by the elements of the family or
Yes.
sets?
Yeah, it's to make it as in the slides. I should actually.
It's better, I'm sorry, it's better to use the upper part of the whiteboard.
Great, great. Anyways, I wanted to erase it, so it's. Well, it's úžas. Yeah. So this matrix, it's indexed by all the k-1 element subsets. And the columns are indexed by the subsets in F sub 0. So F, I don't want to put them names, but it's. So all the sets which don't contain the element 1. And now what I was saying, that if you look at a k-1 element set G, which you actually, for some F1, G was a subset of F1. So you obtained, that means that G was simply F1 with the element 1 removed. So I should write it that way, since Andre told me that it's better to use it here. So if G is of this form for some set, then actually G and the intersection of of an arbitrary set, say F, G intersection F is the same as 1 union G intersection F. Because adding this element 1 doesn't change a thing because it is not contained in F. So therefore, our condition that none of these sets is empty, that's the intersection property, so it is not empty either. That means that for all those G's that we have used already, which already became some small stones in that bag, this row will be completely 0. So we can just forget about those. And what we need to show is that the remaining, that's a matrix of full rank. If a matrix is full rank, then of course for every submatrix of it, it will be similar. So we will have this whole condition, and we can make a one-to-one map from the subsets which are indexing the columns into the remaining subsets that are indexing the rows. And that will be the end of the proof. But, well, it would be nice to have a self-evident proof for this, but actually we use some linear algebraic statement from an old theorem of myself and Wilson, but one could also use some different result by Katona. So it can be proved, but there is some cheating if you want, because the proof is, I left it there, because the proof itself is relying on some linear independence which one has to prove independently. But I like the idea anyways. So I'm going to speak about something more complicated, but as a matter of fact, I was in Palanga last week, and I thought that at the banquet I should do some juggling. So but after all, the banquet was in a restaurant. It was not such an atmosphere. Но у меня есть булавки, я думаю, что надо показать вам. Вот это 3 булавки. Я могу вам показать что-нибудь очень тяжелое, очень сложное. Very difficult. Doing it on 1 foot. I'm just joking. Let me do something a little more. Oh, good. So, спасибо. А теперь на подбородок. Оп. 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 Не мне говорить, это только белые. Это неправда. То желтое. А красная, как она будет? Вот. А теперь все. Но теперь я иду. Вот. Как? Извините. Как сказать? Надо пользоваться ногами. Оп. Что случилось? Я думаю, что вот я успел. Но на другой стороне можно. Wow. I'm impressed. Это не случайно. Это надо тренировать. Вот обратно. А теперь, как в математике, я могу показать вам математику. Вот, по крайней мере, числы. Вот это 1. Каждая булавка, она ротирует 1 раз. Так это 1. А вот следующее это 2. А теперь 3. Помогите считать. 3. А теперь один вопрос. Сколько раз вместе? How many times did they turn all together? Not that I would know the answer. So, а теперь 4. Вот красная 4 раза. Еще раз. А теперь более сложное. Вот 5 раз нет. Самое сложное число это 0. That was the last invention, last number invented by Indian mathematician. So it's 0. А вот fractions, половина. Но у меня, как вы видели, у меня есть еще один. Но. Это, конечно, возможно, но не так удобно. Вот 2 с левой рукой, 2 правой рукой. So, 4?
You prepare for complex number, you have to...
I see, no, just 2 plus 2. Сколько это будет? А теперь что-нибудь я не очень могу делать, но я попробую. Я хочу делать остальное. Спасибо. А теперь мы можем. Let's continue. So, well, since we have already numbers speak, it is not just that we can speak about whether 2 sets intersect or not intersect. We can speak about numbers. So I fix an integer t, which is at least 1, and I define this property that a family is called T-intersecting if any 2 of its members intersect in at least T elements. So what is the easiest way to construct such family? Well, the easiest way is probably to take just T elements and take all the sets which contain all T of them. But if you do it that way, then how many sets will you have? You will end up with only 2 to the n minus T sets, which is not so much when T is getting larger. So, a non-trivial and important classical result from the old days, which was proved by Katona. He proved that the best thing you could do is the construction I have put over there. So if you have sets of size n plus, of size more than n plus t over 2, f and g, they are both of this size. You don't need that. This unit here, f and g, they both have cardinality that is that much. Then of course, f intersection g, which has size equal to f plus g minus f union g, and this is at least then n plus t over 2, n plus t over 2, so adding up to n plus t over 2 multiplied by 2, and this can never be more than the whole set. So it is, and that is exactly t. So that is the construction which was conjectured by Erdos to be optimal, and Katona proved it. I state actually his theorem in a different way than he states it. For the odd case, when n plus t is even, this is the best thing to do. But if n plus t is odd, then the best thing is basically you just forget about one element and guarantee this intersection property on the remaining n minus 1 elements, and then you add or not add this extra element. So, and if t, especially if t is fixed and n is tending to infinity, then you will have still almost half of the sets. So this family is having, if t for t fixed, the size of this family is 1/2 plus little o of 1 n to 2 to the n. So you have almost half of the sets. While if you would have taken all those which contain t given elements for say t equal 10, you already have less than 1/1000 of all the sets. Well, after some point in this extremal set theory, it turned out that it's quite natural, and not just natural, for proving theorems for one family of sets. It's often very useful to consider actually problems for two families of sets. And I'm going to speak about that later. Before I mean, some of you have read it probably, that what I did actually prove, it was a conjecture of Katona, and it was actually funny that he's very much an orderly person. It was in 1974 that there was some big conference which was organized by NATO. You know, all these crazy or stupid or unfriendly organizations, they all want to be popular, so they do something, they show that they do this for science. I don't know how it is in Russia, so I don't want to say anything about that, but I know that in many of my friends in the United States, they had sometimes grants from the Air Force or some other things from the Army and so on. So they are giving away some grants, and by that they are kind of more popular. But of course, once you get a grant from the Air Force, you have nothing to do for the Air Force. You just prove the same combinatorial theorems, but they just give away a few grants just to make popular. So there was a big conference organized by the NATO. And Katona, he was invited as a main speaker, so he absolutely wanted to go. And it was in Holland. And he applied for the Academy of Science, and they refused it. Hungary was just like Russia, a socialist country, so how could he go to a conference organized by the NATO? So, but he really wanted to go, so he went anyways. I mean, he didn't he applied for a tourist visa and then by a tourist visa to Holland and then participated at the conference.
It was not like Russia.
Yeah, I guess. He was not arrested for that. And so but in any case, for that occasion, he had to write a survey paper which was full of problems. And before he left for Holland, he gave me a handwritten form of his survey paper. Those days, copy was difficult. So he had the secretary type it, so that he took with him, and the handwritten copy he gave to me. And so in the summer, I had that with me, and I read the whole thing, and I proved some of his conjectures. And one of them was that, and that became my first theorem, which was published in 1975, actually. I guess that the major part of the audience was not born at that time. That's how old I am. So, too bad for me. And the statement is very simple. The statement is that we have still the same condition, that F is a T-intersecting family, but we added just one extra condition, namely that the union of two sets cannot be the whole set. And the statement is that the best thing you could do, that you take care of this condition separately. So you take, say, the element n, and you never put it in any set. And on the remaining n-1 element sets, you do the best which is possible for T-intersecting families. Now, as I started telling you, for some inductive proofs, it's very useful to have statements for two families of sets. And if you have two families of sets, then, of course, one possibility is always that one of the families would be empty. And then mostly the conditions will be just completely trivial, because if you have an empty family, that satisfies every condition. For the empty set, many things are true. And how to deal with that, the idea is that maybe Péter was one of the first who used it for some theorem of this type, but in any case, that you don't speak about the sum of the sizes, but you speak about the product of the sizes of such families. And in that case, if you take the empty family for one of your families, then you are really punished. Then the product will be 0, so it can't be worse. And now, this Matsumoto and Tokushige, they were my first students at Tokyo University, and I gave them this problem, and they solved it very nicely, and I proved the theorem as it stated, that it's mostly, if you have this cross-T-intersecting property, which meaning that one set from here and one set from the other, they always have to intersect in at least T elements, then still, basically, the best thing is that you take Katona's families for both of them. Or maybe in the even case, in some smaller cases, when T is fixed and n is not so far from T, then the best might be that you take two of your families, one of the, just slightly, when Katona's construction was not symmetric, then in that case you take the symmetric construction, which is close to it from one side and close to it from the other side, and use that. Well, anyways, I wanted just to tell you a recent result of myself. That's what I'm mentioning it. So I just, whatever this minimum is, I denote this minimum by P of nt. And what I could show is that actually, if you take this cross-T-intersecting property together with the condition, again, that one set from here and one set from the other, their union will be never the whole set, then the product will be at most, and I have forgot to put the square over there. No, the product was P of nt, so that's fine. So it's P of n-1t, meaning that for that problem also, what I could prove that is, you just have to take care of the condition for the union condition by saying no, you don't take the element n in any of your sets, and on the remaining you do whatever you had to do for this Matsumoto-Tokushige theorem. On the other hand, if you are going into higher numbers, then still this is my conjecture from 1975, which is still, unfortunately, basically no progress was done. And the condition is that if you had T-intersecting family, then the dual condition will be this S-union family, that the union of any two sets has size at most n minus s. Indeed, if you would take, instead of each set, the complements of the sets, then for them it would be just S-intersection property. So it is very natural to believe that it's, if you have these two opposite type of condition, one condition is about that you have sets that have to intersect in at least in a given number of elements, and the other condition is the opposite type, that the union of any two has to be of size at most n minus s, so that you would divide your set into two parts. So my hands are already blue, so now they will be red too. And then I only need white to be a Russian flag. So if you have this whole from 1 to n, and then you, at some point you break it into two parts, and the first part you take care about this T-intersecting property, and then the rest you take care of the S-union property, and you take all the possible combinations of these families. So that was my conjecture, and that is my conjecture. I still believe it is true, but unfortunately no progress was done, and it seems to be very difficult. And I propose also this more general case for the T-intersecting and cross S union property. So let's move on. I'm also kind of looking forward what is on the next slide, because I, of course, don't remember. I just wrote them on the airplane from Seoul to Moscow. So, well, actually I'm going to speak about a very natural and very old and classical problem of Paul Erdős. Namely, I define the independence number, I pushed the wrong button. The independence number of a hypergraph, just as for the graphs. So an independence number is the maximum number of, say, R, such that you can find these edges in this hypergraph which are pairwise disjoint. Well, in graph it would be just the normal edges. Here they are usually bigger than that. And now, let me give you a construction for such families which have independence number bounded above by some, did I give it, say by R, yeah. I do it for the K-uniform case now. And well, the condition is always the same type, that you take an integer I, and you take I times R plus 1 minus 1 elements. So this always actually denotes the elements 1, 2, 3, etc. until I times R plus 1 minus 1. And our family consisting of all the sets which intersect this set in at least I elements. Obviously, if you take R plus 1 of them, then counting with multiplicity, they contain at least R plus 1 times I elements, which is just one more than this set itself. Therefore, such a family will always have independence number at most R. And Erdős conjectured in 1965 that whenever the problem is non-trivial, because if you had less than that many elements, then you could, in your hypergraphs to start with, you couldn't have R plus 1 pairwise disjoint sets, then the best thing is either A1 or AK. Well, what about the middle ones? Well, the middle ones, they are very nice as a construction. Actually, they were defined by me. But they are, this is, if you check it, this is a convex function. So the maximum is either at some of the ends. So either A1 is maximum, AK is maximum. And Erdős proved it indeed that if n is sufficiently large with respect to K or R, then the best thing you can do is take F to A1. And that's the only extremal construction. So A1 is, we need A1 is the easiest construction. A1 is just means that you take R elements, the first R elements, and take all the sets F of size K, which intersect. Well, I have several ways of denoting it, so it's for this interval, which have non-empty intersection with this interval, so which contain at least one of these R elements. So that's even more obvious without counting, you know, that you couldn't have R plus 1 sets. One contains element 1, the second contains element 2, etc. If you have R plus 1 of them, then 2 of them will contain the same element by the matchbox principle. So it's this is a good construction, and Erdős proved that this is for n very large, and his bound was rather, for this n0 kr was really rather big, then that is best possible. And what I have proved recently, and this appeared this year in Journal of Combinatorial Theory A, and that actually I proved Erdős's conjecture with just a little factor of 2. So instead of k times R plus 1, where it is not true actually, because in the beginning the A sub k is bigger, but when it is at least 2 times as much, then Erdős's conjecture is true. The proof is actually surprisingly short, so if you have some time and interest, I would recommend you to read it. And some small cases are settled. The case k equal 2 already follows from a theorem of Erdős and Gallai. And for k equals 3 and R very large, it was proved by 2 Polish mathematicians, Luczak and Mieczkowska. Their bound for R sub 0 is rather very large, super exponential. And then I succeed in incorporating my personal proof for this Erdős-Gallai case and some of their ideas, and now it is fully proved. Actually, I didn't submit this paper, but more than a year ago I put it on the, what is it called, run by Yale University. There is this part, you can put all your papers to show on a kind of a home page of, как называется по-английски? Думаю, что вы знаете. You put your paper electronically, you don't submit, but you can put on this. Archive, yeah, archive, sorry. So I put it on the archive. So if any of you has the time and the energy to read it, it's rather long. It's over 20 pages of proof. And so this, for the k equals 3 case, it was a lot of work and a long proof. But through that I had some ideas, and I actually worked to get Erdős's conjecture almost. The reason I was actually working on it is that it turned out that they are kind of relevant to some other problems, which I have no time to speak about. Some other people's research, and they asked me that couldn't I prove this and this because they would need that, and so it's not only one, but actually several problems. So actually, that's also some motivation that I do believe that if there is some theorem which is kind of simply stated and nicely proved and non-trivial, then with time there will be some application for it. So if such a beautiful object exists, like a nice theorem, then there should be some use of it. So, in any case, I think I will speak a little bit about the non-uniform case. So now we were speaking about k-uniform families, but we can still speak about the same problem, that the independence number. So what if the independence number is bounded by some number? So that's R, we have been using the letter R for it. Well, in some cases there are natural constructions. Just like in Katona theorem for n plus t odd, we had a less natural construction, but n plus t even were very natural construction. And here again, for some cases when this construction, I wrote there this construction, k sub t, which is all the k subsets which have size which are bigger or equal to t. I mean, it's a very natural construction. And this construction gives us a family which has independence number at most r, as long as n is less than r plus 1 times t. So the last time it happens is that when n equals, just in Kleitman's theorem, r plus 1 times t minus 1. When we have the sets of size at least t, no k plus 1 of them can be pairwise disjoint. And it has, we have Kleitman's theorem from 1968 that is actually the best possible. So you couldn't do any better. It's for this case. And also, Kleitman succeeded in proving that for n equals r plus 1 times t, the best is twice as much as this one. Well, twice as much is always you can do it. If you had a family of sets on this, say on the sets 1 to up to n, here were your sets, many of them, and with this property that the independence number was r, then obviously if you define the family say F star by all the sets and F union n plus 1, where F is in F, and add to them all the sets in F, you would still have a family which is having no R plus 1 pairwise disjoint sets. And F star is having exactly twice as many sets as F does. So this definitely shows us that it is when you increase the number and the size of the ground set, you can always have at least twice as much. But in this particular case, Kleitman proved that twice as much was the maximum you could have. Now, unfortunately, for other congruence classes, if you divide n by r plus 1, they are altogether r plus 1 congruence classes. For other classes, his proof didn't work. And it's only one case, the smallest case which was open, the case r equals 2 and n congruent to 1 mod 3, where it was later solved by a student of Kleitman in his PhD dissertation. I never saw the paper appear. I saw the dissertation, I didn't quite read it. So what I did and what I want to tell you about is that I found some generalization of Kleitman, which will be of not for one family, but several families, R plus 1 families, which will imply Kleitman's theorem. And at the same time, it will be optimal for all values of all modular classes. So all class values modulo r plus 1. So let's me tell it to you. So for that, since I'm speaking about r plus 1 families now, I have to make this definition. I call this family cross-dependent. If you cannot choose r plus 1 sets 1 from each of them such that they are pairwise disjoint. So obviously, if you would have f sub 0 equals f sub 1 equals f sub r, then this is exactly the same as having independence number at most r. And now if I fix this residue class as it's written over there, then and define the families. You remember before we had this k sub k, which were all the sets of size at least k, and some of the sets will be of that form, and some of the sets will be of the form that all the sets of size k plus, at least k plus 1. And I have carefully chosen the numbers so that if you take r plus 1 of the sets and add up these k's and k plus 1s, you will go just to at least n plus 1. So you would never have, in that construction, you would have never this cross dependence will be satisfied. And my theorem is that that is the best you can do. So, and this does imply Kleitman's theorem. So I'm still going to talk, yes, about some problem which I like very much. But before that, I thought I would also show you some magic. Actually, I learned juggling from the American mathematician Ron Graham. That was at Erdos' birthday conference that he showed me how to juggle. And I want to show you a juggling trick which I also learned from him. Not juggling trick, a magic trick that I learned from him. By the way, he wrote with Percy Diaconis a book, Mathematical Magic, or Magical Mathematics, that's the title. It's a very nice book. And so we have 5 people in the first row. One of them is sleeping. You think, can we wake him up? Are you ready?
Yeah.
No. Извините, пожалуйста. Но возьмите немного. Так. Я немного положить на... Не один. Просто. Так. Хорошо. Да, тоже.
So you want to prove the composition of this is also of the same class?
Yeah, but anyways, we did this. So let's... Don't show it to me, huh? And now this is about mental power. So look at your card and just think very strongly about that card and try and send me brain waves. Я хочу узнать, какие у вас эти карточки, а я могу... Я стремуюсь. Но очень трудно, я не знаю почему. Сегодня это очень тяжело. Я хочу, чтобы вы мне, как сказать, помогали немножко. Я могу видеть, вот, если это вале, или дама, или король, или 3, 4, но я не могу видеть вот красную. Если это красная или черная. Я вам прошу, что у кого есть карта, которая красная карта, пусть он руку. Так много. Так много. Я думаю так, что у вас карта это 3, 4. У вас тоже красная, да? Ваша карточка это красная, да? Но у вас нет. Но вот у вас там карточка это 8, как сказать, червя. Покажите всем. Вставайте, покажите. А вот у вас карта это 1 крест. А у вас это, как сказать, по-русски, буби 2. По-русски это очень сложно. А вот у вас это буби 4. А у вас это ас креса. 1 креса.
Это червя.
Червя.
Let us make a guess too. Do you have 32 cards in your?
As a matter of fact, you are thinking about a good thing. It's called a De Bruijn sequence, which is for 32 cards. You can do it for 32 cards, but if you do it for 32 cards, the computation is difficult. So it is. So this is an the cards are organized in a more mathematical way. There is a simple recursion for the cards, how to have them, and I have only 31 for that reason. But you can compute the cards by knowing the colors. For the first 2 would give you the color, so like you should think of them as 0 and 1s, and so zeros and red are 0, and 0 would be как сказать? Буби. А 0,1 будет червь. А 1,0 будет тогда крест, а 1,1 будет пик. А потом вот это 0,0,0, это будет 0, и 0 это 8. Так, in the binary representation. If you have a binary number there, so say it would be 1, 0, 1, then it would be 5, and so on. So you can just count it. And by simple recursion, you can compute what is the next card, and then make the computation. So I have other card tricks, but it's probably I have not so much time to show you, so I rather go back to my slides. Yes, we have 20 more minutes. No, about 5 or 10 more minutes. So let's go a little faster. So some of you might have read already the slide itself. It's a very interesting problem, and it also came from some other mathematical questions and from roots of polynomials or whatsoever. But anyways, let's go through it. So you have n real numbers which add up to 0. And you are looking at the sums of them. So for each subset sums, these are called. So you have a subset of the integers, and you add up all the numbers which are with indices that are in A. That is denoted by S sub A. And you are interested that at least how many of your subset sums has to be non-negative. Well, the easiest construction to give a lot of negative sums is that you would take just one. The first, say, x sub 1, it would be, say, n, and all the others, x sub 2, x sub n minus 1, well, I should have put it n minus 1. Maybe. All this would be minus 1. then they add up to 0, and the only k-element subsets which give you a non-negative sum will be those which contain the element, the only positive element. Well, the conjecture, which is in the middle of the page, says that for n at least 4 times k, you cannot do any better. Here I wrote that k doesn't divide n. I wrote it because for the case when k divides n, then actually Manikam and Singhi gave a nice simple argument, some averaging argument, which showed that in that case it was true for 2 times n or 3 times n, etc. Actually, the only counterexample later which is known is that for 3n plus 1, but to make safe, the conjecture is that for n at least 4 times k, the best you can do is this one. And for a long time there was not much progress on that, and then it's usually the case that someone made some proof which was super exponential, and then so some other people improved it a little bit, and then later it came down to something like factorial. And then there is this paper which appeared about a year ago by Alon and Hao and Sudakov, and they proved for 33 times k squared that this statement of the conjecture, so the conjecture is true. And what I want to tell you in a short way is a simple proof that I found for n at least 2 times k cubed. Of course, for n for k more than 20, and so it's this bound is better, but the proof I have is really cute, so I want to tell you. So I ordered the numbers in decreasing order, and we know that was a condition, that the sum of them is 0. And I am looking at particular sums. So which sums I'm looking at? I'm looking at the sum that I take the first one and the last k minus 1. Well, if this would be at least 0, don't forget that these numbers are the smallest numbers. These are at the end of the row. So these are the smallest numbers. So adding to x1, the smallest numbers would be at least 0. Then adding to x1, any k minus 1 numbers, you would have a non-negative sum. So that would give you immediately that you have at least n minus 1, k minus 1. So we go on next. We do it inductively. I go to the next page. The end of the page is not so visible, but just I associate with 1 this last k minus 1 elements, then with 2 the next 2 last k minus 1 elements, then etc. and to I I iterated I times. So these are just pairwise disjoint sets, and at the very end of the row. And I'm looking at whether this number is at least 0. And if for this I, this number is at least 0, what does it mean? It means that because until that line, so until these elements, these are the smallest. So if I replace them by smaller ones, by smaller indices, I will get larger numbers. So therefore, I can replace I by I minus 1, etc. by 1, and this by all the possible subsets of this set. So I basically get that pk in this case is at least I times this binomial coefficient where you have k minus it's a k minus 1 there. So it's some I times something n minus something k minus 1, which is in this n at least 2 times k cube. Actually here it would work already for a few times k squared too. You would have at least n minus 1 choose k minus 1. So if at some point this process would break down, then we would have that the desired bound. So the only case which remains is that if you did this process k times, and it never broke down. So you got all these sums which were less than 0. So you added the first one to the last k minus 1 was less than 0. Second to the next to last k minus 1 was less than 0. And if you did it that way, then what we do actually is that we kick these things out. This last k times k minus 1 elements, we kick them out and look at the remaining set. And in the remaining set, actually, we kick out still a few ones so that it will be of size divisible by k. That's why this ugly definition that you take away k times k minus 1, and then you divide it by k and make it integer part, and then multiply it by k again to get a multiple of k. And you look at this n sub 0. And the claim is that in this case, whenever you partition into k element sets, for each of these partitions, at least 2 of the subset sums will be non-negative. The original proof of Manikam and Singhi was that if n is a multiple of k, then if you take a partition of the whole thing into k element sets, and you look at the subset sums, then at least one of them has to be non-negative. Since adding all those subset sums, you get the sum of all the numbers, and they would give you 0. So there has to be at least one of them which is non-negative. But in this case, it's very easy, and I will leave it to you because there is no time to convince yourself that because I have thrown out all these numbers, all these things which the sum of them was bigger than, smaller than minus x1. The sum of this is smaller than minus x2. The sum of this is smaller than minus xi. So I threw away k of them, and that will prove me that actually out of this partition, this L sets, at least 2 will give non-negative subset sums. And that gives you the bound that pk is, by averaging that pk is at least 2 over L times k, I choose k. And for the choice of n at least 2 times k cubed, you can convince yourself that this will be bigger than n minus 1, choose k minus 1. And that's all what is in the proof. And well, I put some of my favorite open problems, and that will be really the end of my lecture, and so that we can have time for questions. It's the first, this is probably my problem which was most known and which many people wrote about. I personally never wrote a paper about this conjecture, but it's a very, like Richard Stanley is calling it in his book, the diabolic conjecture of Frankl. So he has worked on it a lot, but he couldn't prove it. So it's so simple. Let me make the definition. F is a family of sets. To make it non-trivial, the thing non-trivial, it has at least 2 sets. And it's union clause, which means that whenever you have 2 sets in the family, their union is also in the family. So it's a very, very simple condition. And my conjecture is that in that case, there is always one point which is contained in at most half of the sets. If you take, for example, all the subsets, then obviously every element is contained in exactly half. So there were various people, various ways they tried to prove it, but I think it's no real progress was made. It's up to your generation, I guess. Now, the second I mentioned, this is also a very simply stated problem, and I only wanted to mention simply stated problems, at least the first 2 will be very simply stated. Here we have a convex family of sets, which has nothing to do with convex sets in the plane or in the Euclidean space in general, but it's a similar definition. So the condition is that whenever you have 2 sets, you have these 3 sets containing each other. A is containing B and C, and if both extremes are in your family, then the middle one has to be also in the family. In that sense, it's similar to convexity. And my conjecture is that in such a family, you can always find an anti-chain, which means that no two of the sets contain each other, which has a relative size at least as much as the largest binomial coefficient with respect to the whole power set. So it would be a funny generalization of, I mean, it's going the other direction than most theorems. In most cases, you are kind of speaking about giving an upper bound for a family. But here you want to show that with such a condition, you can always find a subfamily which satisfies this rather natural condition that no two sets contain each other. And about this is I would say absolutely nothing is known. And now, one of my favorite conjectures, because it was actually already in my PhD dissertation, which I finished in 1975, but then I went to France for 7 months and even that I submitted it before, I only defended it, so I only became Kandidat Nauk in beginning of 77. So, but I wrote it in 75, and this is the conjecture. It's it's on the board. It's about this R-wise T intersection property, and I leave it there, and I would ask you that if you have any questions, this is the time. Конечно, могите вопросы по-русски тоже. Yes.
So there are several kinds of, it looks that in many of your examples,
Yes.
a situation like this, there is some natural family
Yeah.
of a given size,
Yes.
and there is a difficult argument needed to show that this is really the maximum of something like this.
Yes.
And also there is a kind of another, like encoding theory on expanders, when it's quite difficult and ingenious construction
Yes.
to get a family of maximal size.
Yes.
Maybe the bound is more simple.
Yes.
The difficulty is another side. So can you give some kind of intuition what makes the things different? Why in some cases the difficulty is on one side and in other cases the difficulty on the other side? Yes.
Well, it's with this intersection type of problems, when you coding type questions are of the type that families cannot intersect in too much. Like, for example, for k-element sets, if you would, so in this, let me call it Erdos type questions, and they are exactly what you are mentioning, that things where the construction is relatively simple. In this type of questions, we have this type of, that F intersection F prime is at least T, for example. For example, that was the T intersecting property. And now the coding type of thing would be...
Symmetric difference, why instead of intersection?
Well, symmetric difference intersection is if you... Now, I'm speaking, let me speak about this uniform case. Uniform case, symmetric difference and intersection, they are very closely related, so it doesn't matter. But in the coding theory case, this would be the case when you have that the intersection of F and F prime is less than T. For example, it is less than 1, then 0, and you can disjoint sets, that's trivial. But if you have it at less than 1, or less than 2, that would be this kind of Steiner systems if they exist for, so it's for k-element sets, and the best construction, which we don't know whether it exists, and in some cases it does, some cases it doesn't, for T equals 2, in general, I can say it for general T, why not to say it, to make it faster. So if you have it for general T, then this condition that intersection is less than T, it means that if you look at the subsets of size T of F and the subsets of size of T of F prime, then it's always empty. No common T element set. Which gives you the obvious bound that your size of your family cannot be more than n choose t divided by k choose t. This is this coding type of bound. You would have the same thing in Hamming spaces, but then with Hamming distances, and you have to divide it by the size of the ball. So and whenever, so the bound is very simple, but we don't know whether it exists, and no one has seen so far a Steiner system for t equals 6. I mean, for a non-trivial case. So it's, and even for 4 and 5, only finitely many are known. So it's, these things are somehow very beautiful objects if they exist. Many of them were earlier constructed by finite groups and the action of simple groups and so on, or coming from projective or sometimes affine geometry. And so they're very nice objects, and their existence we don't know. And somewhere in between lies the problem which I was working on, and later Andrei Rygorodsky was working on, and made very nice extensions of it to if this is the 0-1 case to 0 plus minus 1 case and so on. So, and that in the general problem would be that if you have a subset L of the integers, L is a subset of the integers 0, 1, k minus 1, and you say that your family is a L intersecting if the intersection of, oh, thank you, but it's, Kaziora уже не нужно. So L intersecting means that for any two sets in the family f prime, the intersection of f and f prime has a size, non-distinct elements of size which is belonging into this family, the set L. And this is in a sense, an infinite many problems, and they are, you can get cases where both the construction and both the best possible bound are very difficult to get. And I'm very proud of an old theorem of myself, which I proved exactly 30 years ago, and which says that for every rational number alpha, which is greater or equal to 1, there exists some k, some choice of k and L, such that for L intersecting property, the best possible bound is just some constant times n to the alpha. So for every rational number, you can actually find such a choice of L that the best you could achieve would be some constant time. So I have a bound which is an upper bound which is some constant times n to the alpha, and the lower bound that it is some other constant times n to the alpha. On the other hand, we know and that there are this similar type of excluded configurations, but not for two sets, but 3 or more, which lead to bounds where there is no alpha. Especially, there is now a proof of this way of Semmeredis theorem for arithmetic progressions for some hypergraph to prove that under this condition it will be some little of n to the k, which is, I mean, you know that his theorem is that for if you have constant times n elements out of the first n elements, and n is very big, then you have an arbitrary long arithmetic progression. So it's a very rich topic, and
okay. Thank you very much. We unfortunately our time is left. I'm sorry. I would be happy to listen for this talk for much more time, but unfortunately after this lecture there will be one more, so we have to leave this auditorium. I'm sorry. Thank you very much, Péter, for your very interesting talk.